of this morning. So the idea today is to go over some of the details behind what we call nowcasting, which is an approach similar in spirit to forecasting, but instead of making projections into the future, what we are doing is making projections about what is going on right now due to the details that we discussed yesterday about the time lag, right? The delay between what is currently going on and how long it takes for this information to reach the data set that we can look at. We will go over also some details about seasonality and finally activity thresholds. So some of the things that we have discussed yesterday, we will also go on a little bit more detail, and also showing some examples of how we are tackling those issues currently specifically for respiratory notified cases here in Brazil. So, as we discussed yesterday, we have this time delay between what is the current epidemiological scenario and what we have in our databases. And just to show a little bit, to give you an idea of how this can be quite different depending on the location and the details behind the notification process in different regions. So here what we have is for different countries a representation of for different weeks along the year. So this is from last year, week 29 up to week 16 this year. Each line here, the black line, the golden line, and the blue line, what they represent is how many weeks it took for reaching at least 80% of what had happened on a given week being already inserted into the database. Okay, so at week 32, we see what it tells here is that for the Rio Grande do Sul state, it took at least 2 weeks for us to have 80% of all the cases that were finally registered related to this week. So the first week of first symptoms on 32. We also reached 90%. We also at 2 weeks. For 95%, it took 3 weeks, and so on and so forth. Now, if we look, for instance, at Rio de Janeiro state, it takes about 5 weeks for us to have at least 90% of all the cases that have occurred on a given week to be inserted into the database, and almost 10 weeks to have 95% of the cases already into the database. So, and you can see that it's quite different for different states, okay? And it can vary also depending on a given period of the year. So this gives us, this illustrates what I tried to emphasize a lot yesterday about the importance of fitting our models, whatever model that we want to run that model specifically for each location, because the details, the characteristics can vary a lot from place to place. And not only that, what also is highlighted here, at least for some states, is that also not only certain characteristics can change from one place to another, but in the same place, it can also change from one time to another. So if you have a model that have some parameters that are fitted to the data, what is going on here gives you the indication that, well, you should also be adjusting your model frequently, right? Rerun your model instead of just fixing the parameters at one point in time and then running the model with the same parameters fixed from then on. No, this is likely to not go so well depending on the specific region. If you have a situation that it's more or less stable, it's fine, but usually that's not always the case, okay? So, how does this reflects in the data itself? So here is an example from SARI in Brazil from the year 2020 up to week 33, 2021. So the solid line, the solid black line here, is the data up to the end of the week 33, okay, aggregated by week of first symptoms. Each dotted line here, on the other hand, is exactly the same information, but the snapshot by the end of each of those weeks that is marked here on this vertical line. So by the end of week 16, this is what we had. By the end of week 20, this is what we had in the system, and so on and so forth. So you see that it has almost nothing to do with what we have on the consolidated data already, right? Of course, if we look back in time, we have more or less an agreement because it has passed enough time for the old data to be already inserted. But if you wanna know what has been going on in the last 4 weeks, so this period here, for instance, we would say that, well, things are getting better, when in reality, things were getting worse and worse, right? So one way to try to circumvent this issue would be, well, we have in the system the notification date, the digitation date. What if instead of looking at the onset time, if I were to aggregate the data by when it was informed, so when the data was inserted into the database. So we've discussed yesterday the limitations of that, right? Because we are accumulating data from different periods in time. But just to show you how things change, the black dashed line here is exactly that. Okay, so is the number of weekly cases aggregated by when it was inserted into the database. So we have a shift here in our ability to identify when the cases started increasing, right? And similarly, when things start to get better, we also have a significant delay on when we start to identify that things are getting better. And of course, this has an impact on both situations, right? On what I am doing, so policies that I am implementing, and communication with the population, right? And so this is another way to represent the same situation, but this for dengue cases. So if now I fixed myself on a given week and I look, well, what does the data look like by the end of the same week? If I look at this for the same week, 1 week, 1 week later, next week, 1 month later, 2 months, 6 months, and what we have once enough time has already passed. So consolidated data, and you can see that for in the year of 2013, for the given region that was being analyzed here, even 1 month later, I was still very far away from what was really going on. And only 2 months later, I was able to identify that the cases were reaching a plateau, right? So it depends on location, as we've seen in the previous slide. It depends on time. It can vary on the same place. It can vary from time to time. And it can also vary a lot from one notification system to another, from one surveillance system to another, okay? So all those things have to be taken into account. So your model must be adapted, must be ran, must be fitted to the specific disease that you want to study, at the specific location that you want to study it, at the specific time that you are running it. Now, one way to try to organize this data in a way that we can try to provide estimations to what is going on is, well, we can extractify all the cases that happen on a given week in terms of how many of those cases are notified on different weeks. Okay, so this is a matrix in which for each row in my matrix, I have the onset week. Okay, so the event time will be on my rows, and the columns identify the delay in notification. Okay, so for instance, for the first row I have for week 1, first column is how many cases that occurred on week 1 was reported without any delay, okay, on the same week at least. On the next column, with 1 week later, 2 weeks later, so on and so on and so on. So if I sum up over all the columns of a given row, I have the total number of cases that occurred on the corresponding week. Okay? Now, what happens by the end of the current week, T? We only know what has been already informed, right? But all the other columns, they will be blank, right? Because it didn't happen yet. I have to wait for next week to have this information here. So there is this triangle here of my matrix that is empty, right? When I'm looking at what by the end of the current week. Okay, so the blue entries here is what I already know, and the gray one, the gray region here, this triangle, is what I need to know in order to understand or to have how many cases have occurred at week T. Okay, so one way to to assess this is try to assess the situation as well. How can I come up with a way to estimate the entries of each entry of this triangle here, right? If I can estimate those entries, then I am estimating what is going on in each of those weeks, right? So, of course, the amount of information that I need to estimate depends on how far ahead I am in time, right? For weeks that have already passed a lot of time, the information that I don't know will be very limited, right? So it should be easy, and the systems would likely be very accurate. So, what we call nowcasting is exactly this estimation. So if I can estimate that, this is what we call nowcasting. So we are providing estimates for what has already happened or is currently happening. Now, if I move forward in time in this matrix, then I will be in the realm of forecasting, right? Of course, I could do forecast exactly on the same way. The thing is, now the amount of information needed becomes more and more. So the accuracy will likely be lower and lower, right? Now, so one way to try to work with that, well, so I can propose a structure here that, well, each of those entries, the cell, the number of cases associated with week T reported with D weeks of delays, with a delay D, it follows a negative binomial with some structure. Why a negative binomial? Only in order to have a distribution in which the dispersion is associated with the mean of the distribution, right? So in the end, what I want to know is the expected value, right? So the mean of the distribution for time t and delay d. And so I have a model here. I can structure a model in which I have a mean mu plus a parameter which is depending on the current week, right? So on this parameter here, it will be in the end capturing the structure of how, if the cases are increasing or not, and then another parameter which is associated with the delay structure, right? So here is the impact of the delay itself, and on this parameter here, I am capturing the structure of the epidemic situation itself, okay? So I'm separating those two. So this is an article a paper that we published with this model. This structure here also we proposed based on things that were on models that were implemented for actuary studies, because more or less a similar problem is faced, for instance, for by insurance companies, right? If they need to know the amount of money that they need for a given month, right? In terms of, well, how many occurrences that they will face and they will have to pay. But what is going on this month, they will only know later on. Only after the individuals have make the claim to receive the money to the event that has already occurred. So it's a similar problem, and so this is something that was already in the literature, so we adapt their model to this problem in particular. So, and then what we do is to run this model and fit different several curves. So we estimate those parameters, and then we simulate this process. So we construct 500, 1,000 trajectories, and then we calculate on those trajectories what is the most likely scenario for each week. So we have not only an estimate, but also the uncertainty associated with that estimate. So for this is an example for dengue cases again, and in 2013. So it's associated with this. Exactly this situation. So the red line here is the currently reported cases. So what was in the system by the end of the day. So the information that was used to run the simulation. The dotted line is the median over the simulations, and the gray area, the gray shaded area, is the uncertainty associated. Okay. And the solid black line is what was actually happening at that time. So you can see that for this particular week, the model was pretty accurate to what was going on, even though the data itself was very far away to what was currently happening, right? Now, for the snapshot that I showed related to SARI in 2020 and 2021, so this is what the snapshot of the information that we have, and then the dotted lines, the information by the end of different weeks, and here are the estimates provided by the end of each of those same weeks. And we can see that again, the accuracy in general is pretty good. Of course, it's pretty good. Of course, not always my estimates will provide a good correspondence with what was going on, which is expected since it's a statistical model. But what is important is that most of the times, even though we might be not that accurate in terms of the volume itself, so the number of cases itself, but at least we capture the trend correctly, right? If it's going on, if it's going up, if it's stabilizing, or if it's on a downward trend already. Now, since we have not only a point estimate, but we have a set of trajectories, one thing that we can do as well is, well, instead of just looking at the median, I can also, by making use of the set of trajectories that I have, I can also calculate, well, what is the likelihood of the trend itself, right? Because it's one thing for us to look at this data, especially with the comparison to what had already happened, to see that, well, here cases were going up, here they were stabilizing, and so on and so on. But if you have to make a political decision, and what you have is this, let's assume that the black line here was the estimate as well, okay? And you have this, this uncertainty here. How assured can you be, and how certain can you be in telling and making a decision, actually, that, well, I have to implement certain measures because cases are going up, or now that the cases is not, the situation might be very extreme, or it still might be in the beginning of the ascension phase. So at the political level, the fact that we have this uncertainty here, because in this situation we can argue that is somewhat clear that cases are going up, so some things must be implemented, but this is not always the case, okay? The uncertainty might also have some of the trajectories could have been showing a small downward trend here, and what do you do? So to have only the median here and the uncertainty, depending on the situation, might not be enough for making a clear-cut political decisions that will have political consequences as well, okay? So what we can do is, well, since we have a set of trajectories, we can calculate what is the likelihood that cases are going up or the cases are going down, okay? So one way to do that, one approach could be, well, I can so let's say that I have so I have this set of trajectories here. How could we propose a model, right, to come up with a way to estimate based on each of those trajectories if cases are going up or down? So let's say that you have a single curve, okay? What would be one way to come up with a mathematical structure which could assess, looking at this curve here, having the data associated with that, so all the points here. Right? So one way is to calculate the slope, right? And how can we calculate the slope? We can, for instance, take a chunk of the data close to the ending point, and, for instance, fit a straight line, and then calculate the slope of this line, right? So one way is to fit a linear model to the data on a window that is close here to the ending point, to what's going on right now. Of course, the bigger the window, the less accurate using a linear model will be to what is going on. But if I take a small window, this approximation might not be that bad, right? So this is exactly what we did. So we proposed an approach in which, well, we have a short-range trend estimation, which is based on the last 3 weeks. So in this case here, we will take only the last 3 points of each of those trajectories, okay, and calculate for each of those what is the slope A for, let's say this is sample 1, sample 2, 3, 4, 5, and 6. So I'll have slope A1, A2, A3, A4, and so on. Okay, those are the slope of row 1, and so on. Then, so when the slope is above 1, things are going up. If the slope is above 1, is above 0, is positive, cases are increasing. If the slope is negative, cases are decreasing, right? So what can I do? I will have, since I have a set of estimates for a set of trajectories, I will have a set of slopes, and then I can calculate, well, since I have a set of slopes, how many of those are positive and how many of those are negative. This is an estimation of, well, how likely it is that cases are going up or down. If 95% of the slopes are positive, well, there's a very strong chance that things are going bad, that cases are going up. If more than 95% are negative, this is a strong evidence or a suggestion that cases are going down. Simple as that, right? So what we have there is exactly this proposal. So if more than 95% of the slopes are positive, I say that, well, the probability that the trend is upward is higher than 95%. So this would be a strong indication that the trend is positive. Then I can have a moderate indication of an upward trend if, well, not more than 95, but at least more than 75% of the slopes are positive. If on the other way around, if the vast majority are negative, I will say that I have a strong evidence of a downward trend. If at least 75% of the slopes are negative, I say that I have a moderate indication of a downward trend. If neither is going on, if I don't have more than 75% positive, or I don't have more than 75 of them being negative, what I say is that, well, the situation is either of stability or of oscillation, okay? Because I don't have any strong indication that it's going up or down, okay? Now, since we have seen already that the data is very noisy, to have only a short-range assessment might not always be a good indication of the stable situation, right? Because we have seen already that we can have, even when in oscillating phases, we can have short periods of increase, short periods of decrease, and even when cases are going up, we can have small fluctuations around that upward trend, which would suggest that cases could be going down when in fact they are still going up with just small oscillations. So in order to try to compensate for that, instead of only looking at this short trend, short time window of the last 3 weeks, we can do the same, run the same approach for the last 6 weeks. So now I have a long-range estimation as well for the trend. Of course, for both in both approaches, we have its ups and downs. So with the short term, I can make rapid assessments on what is the current situation, but my confidence on this assessment is limited. On the other way around, for the longer range, I will have a stronger evidence of what is the mass of the movement of what is going on, but it will take longer for me to identify when things are changing, the shift in trends, right? When it changes from an upward to a downward trend, it will take longer for me to identify if I'm looking at a window of 6 weeks and not only 3 weeks. Now, since the weight or the consequences of the decisions are different if cases are going up or cases are going down, what I can do is to balance those two pieces of information depending on the situation. Like, for instance, if, because it's one thing to have, let's say that the long range estimate tells me that things are all either stable or oscillating. And on the short range, I have an upward trend. Well, this is one thing. Now, let's say that what I have here is so different situations of conflicting information, right? Conflicting indicators for the long range and for the short range. The thing is, at the decisions that we will be making is, well, if things are going bad, so if cases are increasing, I should implement measures to try to minimize the impact of the transmission in my population, right? When cases are going down, what I can do is, well, if cases were higher and now the things are getting better, I can now start to lift up some of the measures that I have implemented, right? Because the impact in the near future will become lower and lower, right? Now, the consequence of making a wrong assumption in one situation and in the other are not the same, right? To make a wrong assessment when cases are getting higher and higher, to say that, for instance, I don't have to do anything because cases are going down when in fact they are going up, is one thing. to say, on the other hand, that cases are going up when in fact it's already starting to decline, it's another thing completely, right? The impact of those mistakes are completely different, right? Because on the one hand, I'm doing nothing when people are getting infected, and on the other hand, on the other situation, I'm still applying measures to minimize transmission when cases are already getting lower and lower. So less and less people are getting infected. The weight of this wrong decision is completely different, right? So this is what I have to take into account when I have these conflicting situations. Because, for instance, in this situation here, when in the long range, the indication is that cases are still going up, and the short range cases are starting to go down. If I maintain here, maintain my measures to avoid more cases, I'm doing too much for population protection, right? So the weight of this mistake is somewhat lower. I might have, of course, economic impacts if, for instance, the measures that I'm implementing is social distancing and so on, limiting some activities. But still, in terms of lives, I am being more conservative. On the other hand, here, if I say, well, in those two situations here, what might be happening is that cases are in fact starting to go up, and I'm not doing anything. And then if cases do in fact increase, and I didn't do anything, I made a mistake of not providing sufficient care for my population, okay? So in this case, the recommendation is, well, wait for at least going from here to here. Well, no, sorry. Yeah. No, in this situation here. In this situation, one recommendation as well would be, well, don't start lifting up any measures already. Wait for at least the situation to come to either one of those two, to then having a stronger evidence that, well, yes, in fact, now I'm having a reversal on my trend, right? So you should look at the history as well. So what was, if at this current week, this is the snapshot that I have, what did I have on the previous week? Of course, the long range should still be up. If it was here, or if it was like this, any of those, well, this is an indication that things are still more or less uncertain. If from week 1, week 2, I have one of those, now I have a stronger evidence that, yeah, yes, I do not need to go further on my measurements. I can start already to think up on, well, what can I already start lifting in terms of preventive measures, because now I have a stronger evidence that cases are not any longer going up, but they are at least reaching a plateau, and it might be, in fact, starting to go down. On any of those, on the other hand, this should trigger at least some level of alert, because things might be already starting to go up, okay? So if I will put more weight on the short range or on the long range depends on the combination of the two, okay? If this conflicting information leads to a more severe situation or a more tranquil situation, let's say. Okay? Always having a conservative mind in terms of prevention. So what we have on this panel here is exactly the history of the long range in blue and the short range trend estimation in red. So we have not only the time series with the nowcasting, but we also have the trend estimation, and then combining those three, I have more evidence for policy making, for decision making. Okay, and this is the main goal in the end of the day. Now, this is for the aggregated data for all individuals in Brazil, for all age strata. And this is, in fact, the snapshot of right now. Okay, this is the data from Monday with all the cases that were notified up to the end of last week. Now, if we look at different age groups for that same data without nowcasting, so the solid black line here is the cases as it is in the database. So in this gray region here is just an indication that, well, for those weeks here, cases are most likely to be incomplete, right? But we can see clearly that, well, the epidemiological scenario for different ages is very different, right? And also the colored lines is the cases based on lab results. So the the light blue here is cases, SARI cases positive for RSV. The dark blue is rhinovirus. The green is influenza A. And the golden line is cases positive for SARS-CoV-2. And we can see that, well, the picture that we have here that is cases increasing since the beginning of the year is pretty much what was going on in young children, mainly due to RSV and rhinovirus, right? But it's not what was going on with adults and the elderly population, right? So this has also an impact in decision making, right? Because in this situation, I'm facing an impact in terms of hospital care at the level of pediatric beds. This is one thing. This is for adult population. It's another set of infrastructure in terms of medical attention. So to also have been able to stratify the data for those different ages is also very important. Not only because of the age that is affected, but also because due to what is the virus associated, right? So what we have been doing as well is, well, the model is exactly the same. The only thing that I have to do is to separate the data for each of those age strata, and I can run the same nowcasting model for each of those age groups, right? So now I know what is the situation for each of those groups. So what you can see is that for children and adolescents, I'm already in a strong indication of that I have already reached the peak of infection, and it's likely that on the next few weeks things will start to get better. For the very young children, cases are still going up, but it's already decelerating at least. And for the elderly, it's still in the beginning of the ascension phase. Okay. Well, and combining those information, so from the trends, we can then also build infographics to, again, try to facilitate or make it easier for, for communication with the population, and also at the terms of decision-making, in which we have for each state of the country a representation of each state colored by those trend estimates for each of them, right? And both for the short range estimation and for the long range estimation. So we make it easier for situation assessment. This is the analysis at the state level, and this is the same analysis now stratifying the data, limiting the data actually, only for the cases associated with the capitals of each of those states. And you can see that not always the situation is the same, right? What is going on at the state level is not necessarily what is currently going on at the capital of the corresponding state. So this is in terms of nowcasting, right? So this is already, it's already a lot of information for to make it easier, or to help in terms of decision making. Now, another thing that we discussed yesterday is, well, what about seasonality, right? Why? So, of course, it's pretty clear, should be pretty clear why knowing what is currently going on is extremely important in terms of decision making, but also if I know what to expect beforehand, it's also extremely important in terms of preparedness, right? To, for instance, planning the acquisition and distribution of treatments, coming up with what is the best period of the year to run vaccination campaigns, for instance, right? In terms of structuring my hospitals, in terms of, well, when I should expect more cases so that I should have more beds available, and so on and so forth. And for that, if we can provide information about seasonality, I can use that information for this type of planning. Okay. Now, one thing that we can do, more or less in the same spirit of what we discussed for activity level or epidemic threshold. So for the epidemic threshold, what did we do? We came up with ways to estimating what was the distribution of cases at baseline. Right, so we had a set of the observations, the incidence on all the weeks at baseline, and we looked at the distribution of those cases to try to infer extreme values, right, and use those extreme values as epidemic thresholds, right? We also discussed yesterday that if we look at the whole season instead of only the weeks associated with baseline, we can also set thresholds for moderate activity, high activity, very high activity, and so on. For seasonality, what we want is to be able to have an estimate for each single week, right? I want to know, well, for week 1, what should I expect? right? Will cases be over here, over here, over there? So we can do more or less the same thing. But instead of looking at the whole trajectory, we look at the distribution for each individual week, right? And construct the set of cases for all the seasons that I have, how many cases I observed for the same week in each of those seasons, right? So I will have a set which is the incidence for week 1, let's say, and all the years in my data set. Right. So with that, so if I have the distribution, if it's something like this, then I can calculate what is the mean of the distribution, different quantiles associated with that, or I can, if it looks like a normal, a uniform distribution, I can calculate what is the average and standard deviation, and this would be right away the information of how many cases I should expect at each given week, right? And then, if I have those estimates for each single week, I can combine what is my estimate for a low number of cases, average number of cases, and high number of cases for each single week, and build the trajectory of what is low, moderate, or high. So if I have for each week here, then let's say that let's say this is the I don't know, the 10 represents 10% of the distribution. This is the correspond to the median, and this is corresponding to 90% of the distribution, right? In terms of percentiles of the distribution for week 1. Then I have the same thing here, here, and there. So whatever is below this curve is significantly below what is expected. Here it would be from low to moderate. Here is the region from moderate to high, and whatever is above this curve is higher than expected, right? And this is the snapshot of the seasonality, okay? So if I have that, I can then plot, if I am able to provide this seasonality assessment, then what I can do in terms of infographics, I can plot now my incidence curve with a background that is associated with those estimates, right, with those regions. So I have here, the green area here will be, in this terminology, the success zone, or the region in which cases are significantly below what is expected for that particular week. The safety zone is well between low and moderate. The warning zone is well when I'm already above what is expected, and the risk zone is significantly higher already. So for instance, as we were discussing yesterday, right? So at this point in time here, I was still below the epidemic threshold, which is this horizontal green line here, but cases were significantly higher than what was expected at the beginning of the year, okay? And then later on, even though it was still below the epidemic level, it was systematically above the median, right, here in the region of the warning zone. So this was already an indicator that, well, this particular season might be worse than usual, that what was usual from the historical data, okay? This in terms of comparing to what is going on right now, but even without this comparison, only looking at this seasonal pattern, I can already say that, well, in the middle of the year is when I expect things to get worse. So in terms of organizing my medical care, I should focus attention in ways that, well, when I'm coming closer to this period of the year, my hospitals should be already well structured in order to meet this likely demand, okay? The same goes for treatment, as I mentioned previously. Now, and also, if this was associated only with influenza A, for instance, what does this tell me in terms of vaccination campaign? Since the vaccine takes of the order about 2 weeks to build up the immunity level, the adequate immunity level, what I want is for people to be vaccinated at least 2 weeks before things start to get really bad, right? So I should focus my vaccination campaign before this period of the year. If I vaccinate my population in this period of the year, it's already too late. I'm wasting resources. Okay, cases still happen this year, so there will be an impact, but the impact would be a lot lower than if people were vaccinated in the beginning of the year, right? Because what I need is for people to be fully vaccinated at this time, right? This would give the highest impact of my vaccination campaign, okay? Yes? Yeah, it's associated very high.
The dashed line is overlapped with the red color, and the very high probability is 0. Why?
I'm sorry, what?
We have a interval of confidence or deviation in this first plot, right?
Uh-huh.
The dashed line, yeah.
Yeah. This is associated with the uncertainty of the nowcasting. Yeah.
So there is a possibility in crossing for the red color zone.
Uh-huh.
But the probability is 0. Why?
Okay. So the probability here is in terms of the activity threshold, not in terms of seasonality. So it's comparing to those thresholds here. So the epidemic threshold, high activity threshold, and very high activity threshold. Okay. But yeah, one could also estimate what is the likelihood in falling in each of those regions in terms of seasonality. Absolutely. There's no problem at all, okay? So, and this snapshot here, this structure, was built pretty much with exactly this kind of approach with data before the pandemic, okay? So, for instance, in this case, in this particular case here, the years that were used from the historical data set were those years that are listed over here. So 2011, 12, 13, 14, 15, all the way to from 2011 all the way to 2017. And the cases here were associated with 2018, if I'm not mistaken. Okay. Now, all good and nice until COVID came along. Now, here is a snapshot for the 5 regions of Brazil. So those regions are aggregates of states, right? So all the states that fall on the Midwest, Northeast, North, Southeast, and South of the country. And the golden line here is 30 cases positive for SARS-CoV-2. So COVID-19 associated SARS cases. And the dashed vertical lines mark the years, okay, the beginning of each year. So here's 2020, 21, 22, 23, 24. What does seasonality mean? If something is seasonal, it means that it has at least more or less clear periodicity, right? Are those cases periodic? Not. And what is the impact? They do oscillate. They show an oscillatory pattern, but they do not show a stable period for that oscillation, right? The frequency is not stable. What I mean by that is, well, when the peaks and valleys occur in each year, is changing all the time. And not only that, the distance in time, how long it takes between consecutive peaks, is not also the same. Because it's one thing for the peak not occurring in the same period of the year. It's another thing for it not being with the same frequency, right? Because if depending on how long it takes, let's say that, well, 1 year have 52 weeks, right? If the frequency of my oscillation is not 52 and is not a multiple of 52, then it will occur, even if the frequency is stable, the peak will be observed in different times of each year, right? This is one thing. But here we have both things. They are happening at different times of the year, and the frequency is also not stable. And if the frequency is not stable, does it make sense for me to look at the distribution for a given week? Not at all. Not at all. And there's no way for me to shift, because if I could also define my seasons instead of going from the beginning of the year to the end of the year. I could say, for instance, that my season goes from August to July. It's August to July. From August to July, or something like that. So the definition of the season, there's no problem. I can change that and adapt to what I observe in the data. But if the frequency of oscillation is not fixed, this is completely thrown out of the window. Okay? So it makes no sense for me to build the distribution of observations on any given week to try to estimate what is the seasonality. There is no seasonality, right? And so there's no way for me to do this kind of construction of what is the expected number of cases on a specific week, okay? This is one thing, but still, now, and not only that, we can also see, but this is in logarithmic scale, mind you. Now, if you look at the absolute scale, now this is pretty much the same information, but now it's aggregated for the whole country. So the black curve here is 2020, 2021, 22, 23, 24. So, no seasonality, and also the volume, it's also completely different from year to another, right? If you compare 2020 with 2022, for instance, it's completely different. 2021, completely different. So we have seen already that it didn't make much sense to try to provide a seasonality assessment. What this data is indicating, at least up to 2022, is that, well, looking at that data, since it is changing a lot from one year to another, does it make sense? Is it meaningful to calculate activity levels in terms of high activity, moderate activity, low activity, or epidemic threshold? Not much, right? Because if I take, for instance, 2020 and 2021, and not only that, right? The impact, even if 2022, what especially by the end, mid and end of the year, was a lot lower, is still in those periods in terms of hospital pressure, it was very high. It was already very high, even though it was a lot less than in the previous years. So it doesn't make sense for me to say that, well, this is already fine because it's a lot less than before, so this is a low activity. No, this is by far low activity, not at all. So I cannot use those historical data as a good parameter to what is too much or what is reasonable, okay? So activity level is already, it's also thrown out of the window. But if I look at 2023 and 2024, now things start to look more similar, right? So here is the same information now stratified by region once more, and we can see that not only that, again, there was a lot of difference also in terms of the curves for each specific region, but for all of them, we have the same snapshot. No seasonality, no clear activity pattern, okay? Now, since this was going on for COVID-19, COVID-19 is a very important contributor to SARI cases. What does this tell me about SARI as a whole? I cannot do what I used to do in up to 2019. Now, if I limit my data to 2022, 23, and 24, on the other hand, things start to look a lot better, okay? And especially if still there is no clear seasonal pattern, right? There is a small suggestion, especially in the north, but still we can see that in the beginning of 2024, we had an increase in cases that were not present in 2023, but there is a convergence here in the southeast, not that much, but still things are starting to look like they are moving towards some level of stability. And in terms of volume of cases, from 2023 and 2024, it looks like, well, now we can start to talk about activity level. And also, if we discard the first peak of 2022 in most states and look, for instance, from week 32 onwards, I could also use the data from 2022, 23, and 24 to build activity levels, right? So I can, we cannot provide seasonality assessment, but in terms of activity level, yes, as long as we discard the first peak of 2022. Okay? And luckily enough, if we stratify SARI cases by influenza and by RSV, even for the situation, it's even better. And we can see that if you compare here, the blue line is what is going on right now, right? And the background is the seasonal patterns using for RSV 2019, 2022, and 2024. And we can see that it pretty much went back to having a seasonality, SARI specifically associated with RSV. So if we stratify the data, we can have an understanding of what to expect in terms of RSV. In terms of influenza A also in terms of seasonality, things went back to more or less normal, but in terms of activity, this year it's already a lot worse than what we expect when we use as historical data set reference the data from 2014 up to 2029, plus 2023 and 24. You see, there's no problem in throwing out of the window what happened in 2020, 21, and 22, right? So this is one thing that we should keep in mind. If I have 1 year or a group of years when the activity was completely different from all the rest of your historical data, throw it out. Throw it out. Mark it as an unusual season, and take it away from your assessment for seasonality and activity levels. All right. So whenever, and this goes both ways. If it was extremely high, or if it was extremely below what is expected. So the idea of extreme values, you should also apply to the season itself. If the season was too extreme, completely aberrant to the rest of your data, move it away so that it doesn't affect your analysis, okay? Now, so for influenza and RSV, we can have this data, and for SARI as a whole, even though we cannot provide as of yet seasonality patterns, at least we can have activity thresholds, okay? And we see that they do provide good information, and we can see that for several states in the country, they are already above what is defined, what was assessed as the very high activity threshold, especially due to RSV. And then we can move from this infographic, where we only had the trend, to now having an infographic in which we have the trend, but also the activity level, right? Because now I can inform not only that cases are still going up, but they are going up already being extremely high, okay? It's another thing completely if cases were going up, but I was still at the low risk, like the green indicator on the activity level, right? And again, we can, since we know that that the patterns can vary significantly depending on the age, I can also build activity levels for each of those age groups, right? So now I can also have indicators, well, what is the situation at the pediatric level, what is the situation at the geriatric level, and so on and so forth. and we can do that for each single state. So we not only can, but we should, whenever possible, extractify the analysis in terms of seasonality, activity level, nowcasting, as much as possible, okay? Of course, what is the limitation? The limitation is, well, do I have enough information in order to provide a good assessment? Do I have enough statistical power to extractify the data at the level that I want? If not, then I aggregate it and stop at that. For instance, this is the reason why we don't run this model, at least for SARI, at the level of individual municipalities in Brazil. Because then the cases starts to get too low and my statistical power is completely lost, okay? So there is computational complexity, data quality, and that I should take into account when I'm making this decision of how finely detailed my analysis will go, okay? Well, and I think this is the last slide. So one point that I didn't mention, pass through here. So this analysis here we can do, as I've mentioned, by building the distribution for each separate week. We can also provide this estimation based on estimates for the trajectory itself. This is similar, but is not exactly the same as looking at the distribution at the single weeks, but it's the same idea. And the benefit of that is that now I have a statistical model to estimate what is the distribution behind what I have observed, right? Because then I have more power in terms of estimating what are the percentiles associated with the distribution. Because remember, in this case here, I have only 4 seasons, right? In terms of SARI by RSV, it's 2019, 22, 23, and 24. What it means is that, well, if I look at it each individual week, I have only 4 observations. If I was to look at percentiles with the raw data, I have only 4 points. It's not enough to do a quantile analysis. Well, it's not enough. It has no information. You say that it doesn't have enough information. But if I have a model for the trajectory, this gives me more power to infer what is the underlying distribution for each week. Okay, and this is the idea behind this statistical model. And again, it's more or less the same thing that we did for the nowcasting, right? We have a negative binomial for the distribution of observations at each week t here, okay? And then we look well at the distribution over that. So we have estimates for the mean of the negative binomial, and so we can then once we fitted this model, we can then again generate a set of trajectories, and from the set of those trajectories, then we calculate what is the distribution for each individual week. Okay? Questions? Well, people, so in the end, now that we have here a picture, and one thing that I would like to go back into is, well, during this school, you have seen and you will see more and more about mechanistic models and agent-based models and model fitting to the data. And what I want to highlight to you, as I did somewhat on the first lesson yesterday, is that, well, you have we can then combine, since we have, if we are able to provide nowcasting estimates for my trajectories. Now look, the blue bars here is the cases that have been notified already, so what I have in the database. Here we have the nowcasting. And now if we think about model fitting, so I have my mathematical model for the disease transmission. If I was to use the raw data to fit my model, remember, if I use all the data up to the recent weeks, my model has no alternative other than say estimate that project, sorry, that for the next weeks things will still be going down, right? But what I can do is then combine, instead of fitting my model over the raw data, I can fit my model over the trajectories provided by the nowcasting model. Okay? What is the downward on that? The downside of that is, well, I have uncertainty already on the nowcasting, and this will propagate to my projections once I fit that to my model, right? Especially if I have a stochastic model, right? So the stochastic model will already have an inherent uncertainty, and that uncertainty will be compiled with the uncertainty over here. Because now I'm not running my model 1,000 times over one set of raw data. I am running over a set of 1,000 quote-unquote raw data, right? And then I'll have, what I should do is to combine all the outputs over all the inputs to have now what is my consolidated estimate, okay? So I have a combination there, let's say that from 500 by 500, 500 by 1,000, 1,000 by 500, whatever. But it is the full combination of trajectories that will have will be my final set of estimates. Okay. So the uncertainty is likely to be larger. Well, likely no, it will be larger than the nowcasting itself. So if the nowcasting, it's already, the uncertainty here is already too high, and I know that my stochastic model for disease propagation also have an important uncertainty, it might already make no sense to combine those two, because the resulting uncertainty will be extremely huge, so that the point estimate make no sense at all. Okay, so we have to take that into account before combining those two approaches. Okay, if the uncertainty here is low enough, and my model is also quite tight, it could be fine. Okay, and then of course the ending point is, as always, if you are doing model fitting for a disease that is currently going on, in general, do not go too much up ahead in time. Again, because the uncertainty will be getting higher and higher. Okay, it might make sense to provide projections 2 weeks, 4 weeks ahead, but 1 year, You can have from 0 to 5 million cases. This doesn't make any sense, okay? So with that, I finish what I had prepared for the 3 classes for the school of this year. I hope it was sufficient to give you a glimpse not only of some of the methods that we can use in terms of situation analysis, but also the importance of taking your time into understanding the structure of the data that you are analyzing. This is absolutely central, okay? And the downside is that not always those details are already described into the data set, okay, as a appendix or supporting material or whatever. So if you have the opportunity to discuss with the people which are involved in the process of collecting the data for that particular surveillance, this might lead to very important information that is not written down anywhere, okay? But it's something that is important to try to come up with. Otherwise, you can have a wonderful model which is extremely accurate, but the data that you are feeding it doesn't make any sense. So your outcome will also won't make any sense at all, okay? Well, and with that, I finish, and thank you very much for your attention.